Okay, so today we are learning about logistic functions. I gotta get my notes so I know what I'm writing. All right, logistic functions have two general formulas. One is in terms of E, one is not in terms of E. So it kind of depends on the problem which one you would use. So the first general formula is f of x equals c on the top divided by 1 plus a times b to the x. So if you think about what we've learned already, what does a logistic function kind of remind you of? Where does x show up in the problem? It's an exponent. It's kind of like an exponential. Do you guys see a little bit of the similarity there? It's in a fraction, so obviously that makes a difference. But we do see something to an exponent of x. All right, so it kind of seems a little bit like an exponential. They're fairly similar to each other. The second form would be f of x equals c over 1 plus a times e to the negative kx. Right? So here's a picture of a typical logistic function. If you were to cover up this part of it, it kind of just looks like an exponential function. You guys see that? Exponential, like, grow super, super fast and they go like straight up. A logistic function just says that after it goes straight up for a little bit, the growth decreases and then it levels out. It has something called a carrying capacity, which we'll get to in a second. Okay, so in these formulas, we have a bunch of different letters here. We have an A, a B, a C, and a K. So you can see that A, B, C, and the K is over here. All of those are positive constants. And what I mean by constants is that they are all numbers. They're not considered to be variables. That means for the equation to be complete, those have to have numbers in place of those letters. Always, always. Okay? The B value must be less than 1. So the base of your exponent has to be less than 1. The reason that this is an E, anyone remember what the decimal is for E? Yeah, it's 2.71. The reason that E is allowed to be a base is because this E is raised to a negative exponent. So when they said that K has to be positive, that means there's going to be a negative sign in front of a positive number, which makes a negative number, right? What does a negative exponent do? It turns it into a fraction, right? So even though E is 2.71, when you have E to the negative K, that means you're going to have a base number for your exponent where the base is less than 1. Does that make sense? So you can you don't have to memorize that. I'm not going to ask you a question about that, but that's why the two equations are similar. They both have that rule that whatever the exponent goes with, the base that goes to the exponent has to have the property that it is less than 1. And this holds true in this equation because it's e to the negative k. It's a negative number there. All right, C, the number on top, is known as the carrying capacity. That's probably the only thing I hear it called in calculus, or the most common thing, I guess. The other phrases that people use for it is they call it the limit to growth. Or they call it the growth maximum, or maximum growth maximum. Growth maximum sounds weird. Maximum growth sounds better. All right. So what you'll notice here in the picture is that there's actually a horizontal asymptote down here at 0 always. Every single logistic function you ever look at will always have a horizontal asymptote at 0. So y equals 0. The other horizontal asymptote is at the carrying capacity, which is the C value. Okay, so the second horizontal asymptote is y equals C. The range of a logistic function is always between those two horizontal asymptotes. So the range is always from 0 to c. And we can always describe the end behavior with limits. So what I mean by that is, what does the graph do as it goes left forever? What does the graph do as it goes right forever? Do you guys remember that a little bit from the rational functions? It makes sense we're talking about it again because we're talking about a rational function here, right? Logistic functions are written as fractions. And so that means as you look at the graph, the left side of the graph always goes towards 0. The right side of the graph always goes towards the carrying capacity. So if you look at the limit here, it says as we go to x is negative infinity, that means as we look to the left forever, the graph equals 0 on the left side. As we go to the right forever, the graph is going to equal c, or that carrying capacity. Okay. The context that we use logistic functions in is any situation really where there's a population. So we could talk about the population of bunny rabbits that live in my backyard. We could talk about the population of students at Northern. We could talk about the population of people who live in North Carolina, or people who live in the United States, or people who live in the world in general. So what it means by carrying capacity is you can't have an unlimited amount of bunnies in your backyard. It will not grow forever and ever and ever and ever. There's going to be things that limit the growth of bunnies. For example, your little brother who takes out guns and shoots them in the face and kills them, that is something that limits the growth of bunnies in your backyard. The bunnies running out of food, and starving to death limits the amount of bunnies in your yard. The bunnies running out of food and then eating the weaker bunnies to survive limits the amount of bunnies in your yard. Does that make sense?
Yes.
So anytime you have a population of something, there are limiting factors to that population. Students at Northern do not increase without bound. We have a certain number of seats at our school, right? Classrooms have a limited number of size we can have for students at our school. There's a point where our school would get so big, they would have to build another high school nearby, and then some of our population would go there. That's what happens when high schools get too big, they start to make other ones. Does that make sense? So there's like limiting factors that keep a population from growing without bounds. What this means is that in situations before, when we said like, oh, that thing that we're learning about grows exponentially, we say, well, yeah, it appears to grow exponentially at first, but nothing can really grow forever. At some point, there's going to be a limiting factor that keeps it from growing forever. For instance, if you compare data for how many people live in the world, you would notice that the number of people living in the world actually is starting to level off because we don't have an infinite amount of space in the world. Like, there's a lot of space, right? But we're going to run out of resources, and we can't have that many people. That makes sense? Okay, so this is logistic functions are typically used with populations of real living things because this is how real living things act. There's only so much space. There's only so many resources, okay? All right, so let's go ahead and look at some examples of how to work with these equations. You're going to notice some things that feel a little bit similar to exponential functions. There's going to be some things that feel a little bit different, okay? So here in example 1, it says find the asymptotes, find the Y-intercept, and find the maximum growth. And then after we do those things, we're going to go ahead and sketch a picture of the graph. So what are the asymptotes based on this function?
Y equals 0 and
Yep.
Y equals 11.
Yep. All right, so where did you get y equals 11 from?
It's the carrying capacity.
Mm-hmm. Yep.
Didn't have to raise my hand.
No, you just said it. So the bottom of the graph is always 0. The top of the graph is always the carrying capacity or the limit to growth or the maximum growth. So we already found it, but what is the max growth? 11. Okay. And then how do we find the Y-intercept by hand?
Plug in 0.
Plug in 0 for x. So we're going to say f of 0 is 11 over 1 plus e to the negative 2 times 0. So this is 11 over 1 plus e to the 0, right? Negative 2 times 0 is just 0. What is anything to the 0 power? 1. Okay, so what we really have is we have f of 0 is 11 divided by 1 plus 1, which is 2. So we're going to go ahead and say that our y-intercept is the point 0, 11 halves, or if you want to think in terms of decimals, 0, 5.5. Okay. So you need a calculator to find that information. It's relatively easy to see what those different pieces are. Okay, and then what we do is we're going to go ahead and sketch this again without a calculator. So I'm going to go ahead and draw something like this. I'm going to say this is 5, this is 10. I have a horizontal asymptote at 0. I have a horizontal asymptote at 11. I have a y-intercept at 5.5. And I know it follows the asymptote, it grows pretty steeply, it levels off, it follows the asymptote. That's a logistic function. We're going to go back and label something in this picture up here because I forgot to have us do it. So if you look here, you can see the slope of a picture tells you how fast something is growing, right? If the slope is steeper, it grows faster. If the slope is less steep, then it's growing less fast. So if you can see here, like the slope is getting steeper and steeper and steeper and steeper. So the rate of the growth is increasing. And then here the slope is like constant for a little bit. And then the slope gets less steep and less steep and less steep, so it's growing less fast. So right here in the middle, that is where the growth is the fastest. Okay? Growth is the fastest. And that's because the steepest slope is going to happen right there in the middle. You can see it's almost completely vertical. So that's a really steep slope. That's very fast. All right. Let's go ahead and look at the next problem. It's a story problem.
No. Yay.
Did you say no? No. It's a story problem. No. All right. So it says the number of students infected with the love of math T days after starting Miss Rice's class
0.
is modeled by this equation. That's hurtful. You get an F, sir. How many students were infected before they met Miss Rice? So what are we plugging in for T? We're plugging in 0, right? Because T represents the number of days they've been in my class. So before they've been in my class, that's a 0 value. So what are they basically asking us to find right now? They're asking for the y-intercept. So we're going to go ahead and say f of 0 equals 800 over 1 plus 49e to the negative 0.2 times 0. Yeah, 0. The point is right there. This little thing right here is just the period at the end of the sentence. Okay. All right, and so we know that this is actually 800 over 1 plus 49. E to the 0 is 1. So that's really 800 over 50. How many 50s are there in 800? 16. So apparently before school started, there were 16 students that had the love of math virus. They'd been infected by some previous math teacher. $16 students. Okay. Part B. When will the number of infected students be 200? So what do we do? Is 200 going in for T?
No.
No. It's going in for F. It's going in for F of t. So 200 students equals 800 over 1 plus 49 e to the negative 0.2t. So our variable, we're finding t. Our variable's on the bottom of a fraction. Do we want it on the bottom?
No.
No. So what should we do? Yeah, we need to get this part off the bottom. And I'm going to do that by multiplying by 1 plus 49 e to the negative 0.2t. And when I do that, it cancels. And if I did that on the right side, what should I do on the left side? Same thing. So I'm going to multiply this by 1 plus 49 e to the negative 0.2t. Okay. So I'm going to go ahead and write down what I have. And I want to start moving things away from the t. Divide by 200. So that's an easy thing to move over first. Divide by 200. Got rid of that. So we have 1 plus 49 e to the negative 0.2t equals 4. 800 divided by 200 is 4. Not yet. Subtract 1. So I'm going to say I've got 3 on the right side now. Divide by 49. So I have e to the negative 0.2t equals 3 over 49. And now we're going to ln both sides. So did it start to feel familiar there towards the end? Yeah, like we've been working on this. So we have negative 0.2t equals ln of 3 over 49. Divide by negative 0.2. So t is ln of 3 over 49 divided by negative 0.2. What does t equal? 13.966. What was our units of measurement? Days. So I would just like to point out that I started off with only 16 students being infected with the love of math. And after 2 weeks, I have 200 students in this school who are infected with the love of math, which means not only am I reaching the kids in my room, no, I'm going outside these doors. And students are being infected everywhere.
It's an epidemic.
It's an epidemic of math love. Doesn't that feel powerful? You guys are a part of something here. You're a part of the spread of the infection of love. All right. The next question says, what is the maximum number of students that can be infected? So if we look back at the equation, what is the maximum number of students that can be infected? 800 students. So the explanation for that would be maybe students who skip school are never around anyone who's infected with the love of math, so they can't become infected. You know what I'm saying? Maybe there are some students who already have a math phobia that has infected them, and that is keeping them from being infected with the love of math. There are some students who have had just like such a bad experience they could never possibly, you know what I'm saying? But most normal students would have the potential to become infected with the love of math. Amen. All right, example 3.
This is religious propaganda.
Yeah. All right. Write write a logistic equation in this form, given that the y-intercept is 5, the carrying capacity is 100, and the point 227 shows up somewhere on that curve. Okay? So based off all those numbers, what is the easiest number to plug in? The 100. Okay, let's start there. F of x equals, plugging 100 in for c, so we've got 100 over 1 plus a times b to the x. Okay. What is going to be the next easiest thing to plug in? The y-intercept. The y-intercept is going to be easy to plug in because you're plugging in an x value of 0. And when you plug in an x value of 0 right here, you get b to the 0, which is 1. So if that becomes a 1, then you only have one variable left. That's why we plug in the y-intercept next. It's helpful to have only one variable when you're solving for something. Okay? So I'm going to say that if I plug in 0, f of 0 is 100 over 1 plus a times b to the 0, and I know that when I plug in 0, I get a result of 5, because the y-intercept was 5. Okay, so if we go ahead and we start working on solving this, I just ran out of lead. Guess we're done. Okay, bye guys. All right, how about you guys see what you can do with it while I get another piece of lead out? Anybody? Anybody? B to the 0 is 1, right? So replace that with a 1. And then your variables on the bottom, we don't like that. So what could you do since your variable's on the bottom? Yeah, multiply it to the other side. So a times 1 is just a. I don't like this variable on the bottom, so I'm going to multiply by 1 plus a, and multiply by 1 plus a. So 100 equals 5 times 1 plus a. And how could I start moving some stuff away from the a?
Divide 5.
Yeah, divide the 5 over. What's 100 divided by 5?
20.
Okay, so 20 equals 1 plus a. And so a equals 19. All right, so now we have the function f of x equals 100 over 1 plus 19 times b to the x. That's the function that we have now. We are very close to being done. All we have to do is figure out what the base is, that b value. Okay? So now I can use the information I have where if we plug in an x coordinate of 2, we get a y coordinate of 27. So the last thing I'm going to do is I'm going to say if I plug in 2, 100 over 1 plus 19 times b to the second power. If I plug in 2, I get 27 as an answer. Okay, so we again have a variable on the bottom. What do? Multiply by that whole bottom part. So we're going to have 100 equals 27 times 1 plus 19 b squared. I didn't show as much work that time. Are we okay with that? I multiplied this over to the other side. Okay, and then I think I heard someone say the next step. Yeah, divide the 27 over. Yeah. So 100 over 27 equals the stuff that was on the bottom. Did you guys notice that the 27 and the bottom just switched places? You see that? These two just switch places. It always happens like that, so if you want to do that in the future, you're welcome to. If you're like, what? Then ignore it, keep doing what you're doing. All right, 100 over 27. What do we do next? Subtract 1. This is where I got my calculator out. I'm just not feeling these fractions. 100 over 27, take away 1. That's a nasty decimal. I don't want to have to store the nasty decimal in my calculator, so I'm going to turn that answer back into a fraction. So if we did 100 27ths and we subtracted the 1 over, we end up getting 73 27ths equals 19b squared. And then what do we have to do? Okay, so I'm going to take that fraction, 73 27ths, I'm going to divide by 19, I'm going to turn that into a fraction. Am I the only one doing it? No. Last year in calculus, students used to be like, Miss Rice, you're my calculator. No, I'm not. Freaking plug it in. Lazy. 73 over 513 is what it should have been.
73 over 5.
Mm-hmm. And then, how do we solve for b? We square root it. Yes, because it is squared, so we're going to square root, and so b equals...
I'll find you out. I got you. I just don't like drinking.
We can write the number as a big square root. That's fine. We're gonna do this. The reason we're gonna do this is because we're plugging this into a formula, right? So we want an exact answer. However, how many options do I have here?
Plus or minus.
Plus or minus, right? We don't want to kill any ducks here. We want to be reasonable about it. But now we have to remember about the rules that we have on the front of our notes. So don't flip yours over. I'll flip mine over so you can see it. It says that A, B, and C, and K have to be positive values. So we can't do the negative version. That means we have to do the positive version. So I'm just going to circle the positive. That's the one that's going to win in this case. Okay, so now we are ready to finish writing our equation. Aren't you glad I gave you plenty of space? F of x equals, our carrying capacity was 100. Then we had 1 plus 19. And the b value was the positive version of the square root of 73 over 513. All of that is being raised to the x power. And that was it. They look kind of crazy, don't they, those functions? Yeah. Yeah. Whew. Okay. So, do you guys want to practice that for a little bit, or do you want to see the like heavy calculator stuff? This is just like very calculatory. You want to practice it a little bit? What if we practice for a little bit, and then maybe in like 20 minutes I'll go over this last problem. Just give you guys a little bit of a break, let you practice. It's a Catmobile. All right. I need you to take your calculator, and every single person has to follow along. That's right. What about me? Yes, you. Yes, you. All right. I'm going to go ahead and clear my calculator. So I'm going to hit second plus 7, 1, 2. Second plus 7, 1, 2. It says use a calculator to find a logistic regression model and an exponential regression model for Florida's population from 1900 to 2000. Use 0 for 1900. So that means that this, we're going to use a 0. 1910 would just be 10. 1920 would just be 20. 30, 40. A hundred. All right. Once you have that fixed, go ahead and on here we're going to hit the stat button. You guys see it, stat? And it says edit, number 1. You're going to press enter. Yeah, it's been a while, huh? All right, and we're going to go ahead and plug in the years. So 0, enter, 10, enter, 20, enter, 30, 40, 50, 60, 70, 10. Were we racing there? All right. And then in list 2, L2 is list 2, you're just going to type in Florida. We are not typing in Pennsylvania. Do not type in Pennsylvania. We're only doing Florida. So 0.5, 0.8, 1, 1.5. All right. Check for typos real quick. You'll get very confused if you have typos. Some of you guys who are racing, you especially need to check for typos. I heard you typing that fast. Nobody types that fast normally. All right. Go ahead and hit the Y equals button. Oh, it means you deleted L1. If you clear the if you restart your do second plus L 7 1 2, you should go back.
I just redid it. I cleared it.
I mean, somebody went through and deleted it on accident. I don't know how to fix that, but I'll help you do it with L2 and L3. You'll be fine. So just type them in as L2 and L3. All right, go ahead and hit the Y equals button, and hit the up arrow. So it's blinking on plot 1, and press enter so it makes plot 1 dark. Yep. So now it's dark on plot 1. Now hit the zoom button, and we're going to go down to number 9. Zoom stat. What that means is that it's going to take all the things you just plug into your list, and it's going to make them show up on the screen. Yep. So press enter. Now all those things you plugged in show up on the screen. What? Crazy.
We press what?
All right. I need you to stop talking. I need you to stop talking so I can repeat it. All right. So let's make an agreement here. When somebody asks, instead of 17 people answer, just be quiet and let Miss Rice answer. Okay? All right. So you hit the Y equals button. You do up arrow to plot 1. You make it dark. Then you hit the zoom button, and you're going down to number 9, which is zoom stat, and you're pressing enter, and it will make it so your dots show up on your screen. Okay? All right, just look at Leah's. All right. Next, I need you to hit the stat button again. And hit a right arrow to calculate. And we are going to go ahead, which one does it say? It says Logistic Regression first. So we're going to scroll down until we see Logistic. There it is. It's B. Logistic Regression. All right. And do not go ahead, because then you're going to get frustrated because you're going to have to start all over. Okay, so hit enter. Now, Corday, if yours was working, this is where you're going to have to switch these. It's using L1 and L2 because we programmed our stuff in L1 and L2. You would put L2 and L3. And this is important for anyone. If you accidentally delete one of your lists, you can still do the problem. You just have to tell your calculator which one to look at. The L's are right here above 1 and 2. It's the blue. So that's if you want to switch what list you look at. For us, we want L1 and L2, so we're good. Go ahead and scroll down. It says store the regression equation. What we're going to do is we're going to tell our calculator to take the answer that we're about to get, because what's going to happen is the calculator is going to give us like a line of best fit of a logistic curve for our information. If we want that logistic curve to go straight into Y1 so that we can actually graph that curve without having to type it in, then we have to tell our calculator to go store it over there. Okay? So here's what you click next. Are you ready?
Mm-hmm.
You hit the vars button. Vars meaning variables. So hit vars. Go over to y variables because we want to plug this in for a y value. For function, press enter because this is a function. And we're going to plug it in as y1. If you want to plug it in as y2, that's fine. It's not going to make any difference. Okay? Then press enter. So now your calculator should say L1, L2, y1. Yours should say L1, comma, L2, comma, y1. Yeah, okay. Okay. Well, I'll come over and help you with that. Okay. Once you're done with that, go ahead and press enter. It's asking if you should calculate. You're going to press enter again. It's going to take a little bit because your calculator's thinking. And it's thinking. It's still thinking.
Say that.
All right. I need you to listen carefully. So up here, it's telling you what letters it wrote for the equation. And then down here, it's telling you what those letters represent, okay? So we're going to write this on our paper, and for each thing we write down, we're just going to round to 3 decimal places. We don't have to worry about the perfect answer because we told our calculator to put the perfect answer in our graph already, okay? And I'll show you that in a second. So we're going to write f of x equals, and they gave us a c value, that's the top. What's the c value if we give it 3 decimal places?
48.021.
Okay. And then on the bottom it says 1 plus a. So 1 plus what a value do we have with 3 decimal places? 81.904. Okay. Then it says e, and this to the is showing us it's an exponent. And then it says negative b, so we're going to put a little negative sign. There's my e, there's my negative sign. What do we put for b with 3 decimal places? 0.047x. So there is the regression line, the logistic regression line that fits our data. So if you want to see that, go ahead and hit the y equals button, and you can see that all of a sudden there's an equation that you never typed that's in there. And do you see how many decimals it has? You can just scroll through that. Our calculator's being very accurate right now, and we did not have to type any of that. Do you see that? Okay. Go ahead and hit the graph button, and you can watch it graph over those points. Do you see how accurate that is? Yeah. Yours didn't do that? How did I get this in here? The reason, listen carefully, the reason that it did that is because when I hit stat, and when I went over to calc, and when I went down to logistic regression, I did not just press enter. If I had done enter, 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 it would have given me just the equation. But I wanted my calculator to store it, so that's where I went right here, and I hit the vars button, and I went over to yvars, and this is me telling my calculator to plug it in for y1. So it says, calculator, when you get the answer, plug it in there for me. And so that's why my answer went over there in the graph. And then I'm telling it to do its thing, and right now it's finding the answer for us, but it's also graphing it for us. Okay. So, yeah. Okay, so we're going to use the 2 models. We're going to use the 2 models. We're going to do a logistic model right now. We're going to do an exponential model in a minute to predict the time when the population is 9.7 million. Now, I know based on the table that it's 9.7 million in 1980. I just want to see which of my equations is more accurate. Is it more accurate to model this with an exponential function, or is it more accurate to model this with a logistic function? So that's what we're testing right now, okay? So what we're going to do is we're going to solve this equation. We're setting this equation equal to 9.7, and since we have all those crazy decimals, we are not going to solve this by hand. We're going to solve it by graphing in the calculator. So hit your y equals button again, go down to y2, and in y2 type 9.7. Okay? And then go ahead and hit graph.
Oh shit.
And now we're going to do second trace. Second trace. Number 5. And we don't have to move the cursor any closer. We can just press enter, 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 and it will find it for us. I did second trace, option number 5. So that means that if I solved for x, my x value is approximately 80.179. And 80, see the 80 right there? That's 80 years since 1900. So this is 1980, right? With like a few months in between. Like a month and a little bit. So this is 1980. Is that what we expected? Yeah, that's pretty accurate, right? Okay. All right, now what we're going to do, did everyone get that answer?
I got it. Yeah, 80.179. 303.
Okay. Now, we are going to do the exponential problem, okay? So the exact same thing, but instead of using logistic, we're going to use exponential. So hit the stat button, go over to calculate, go down until you find exponential regression. It's number 0 at the bottom. We got that? Okay, press enter. And I'm going to scroll down. Again, I want it to store the equation for me. So what do I hit to make it store it? Vars, y vars, enter, and I'm plugging it in for y1. What it's going to do now is it's going to replace that equation that we had in y1 with the new equation. Okay? So it's replacing that equation that I had with the new equation. The 9.7 is going to stay in there as y2. All right, because I plugged it in, I didn't replace anything, so that 9.7 is going to still be there. Okay, so we're going to go ahead and write this one down. You'll notice that one went a lot faster. Nope, this one just says a times b to the x. So a is the coefficient of the exponential function, 0.513, times the base of the exponential function is 1.036, and it's to the x power. And so now if you were to look at the y equals screen, you'll see that there's a different equation in your y1 because we just had the calculator replace the old equation with this one. And now if you graph it, you'll see the exponential equation following the points. So this one, when you watch the end of it, instead of it starting to level off towards here at the end, it doesn't start to level off. The exponential problem just keeps going straight up. Do you guys see that? So it's a little different than the logistic problem was. So we're still doing the same thing. We're setting it equal to 9.7 just to see which equation was more accurate. And we're going to go ahead and hit second, trace option number 5. Enter, enter, enter. And so this one says that x is approximately 82.362. And what year is that? 1982. So which curve was more accurate? The logistic one, which makes sense because we were talking about a population of people. And a population of people is not going to grow exponentially. It's going to grow logistically. It's going to grow really fast, but at some point it has to start to level out. So it makes a little bit of a difference. Okay. How are we feeling about that? Okay. Now, it wants us to find the regression model, and I missed a word, the logistic regression model for Pennsylvania. So what we're going to do is we're going to do second plus 712. We're just going to clear all this out so we can put new numbers in. Second plus 712. So for those of you who if we messed it up a little bit and got lost, we can start over and hopefully go with this one. So I'm going to hit the stat button. And again, my first list is going to have the years. So 0, 10, 20, 30.
Oh my God. What in the world?
It's a race. And then for the second list, we're going to go ahead and plug in the other numbers. So this time we're doing Pennsylvania. What? Close call. And if you were racing, you need to check for typos.
Oh, I have a whole typo.
So, yeah, 0 goes with 6.3. How do we get it so the dots show up on our screen? We hit Y equals,
And then
we go up to plot 1, we make it dark. Press enter. Y equals, go up to plot 1, make it dark. Then we hit zoom, and it's number 9, zoom stat. Woo! There we go. Does that look exponential?
no.
Not quite, right? Exponential normally goes like this. This one definitely doesn't quite look exponential. Zoom number 9. Yeah. All right. We are doing.
Mine says error.
You probably have a typo somewhere. If you have an error, typically what happens when you have an error is that if you look at your list, you might have missed a number, so your lists are not the same length, and your calculator gave you an error because you had an x coordinate that didn't have a y coordinate, or you have a y coordinate that didn't have an x coordinate. So, did you have a missing point in there? Yeah, there you go. All right. So now what we're going to do is we're going to hit the stat button, and we're going to go over to calc, and we're going to go down to logistic, because now we know logistic is the right model to use for problems like this.
What did you say?
So we're hitting the stat button, we go right to calculate, and then down to logistic. And I press enter, and I'm using my L1 and L2. Did you trade it for a different calculator?
Yes.
And then down here, if I'm telling my calculator to store it, what do I hit? Bars.
So that's after we hit stack, right? Stack, count.
So this is me telling my calculator, please store it in Y1 so I can have perfect numbers graph. Okay. And then I hit calculate and I wait. All right. And let's go ahead and write it down. We have f of x equals, the c value goes on top, and we're going to do 3 decimal places. So what should I write? 1 plus Nancy, I'll come help you when I sit back down. All right, so our A value is 0.938. E to the negative, right? Because we can see in the equation it has a negative in front of the B. And then the B value is 0.034. Did you guys notice that the calculator uses a different B value than we used? So when we wrote this on our notes, we didn't call it B, we called it K, just so that we're not confused. We called it something different in our notes. And then we put the X right next to that. Okay? And then if we want to see that our calculator really did plug it in for us, we can hit the Y equals screen and we can see it all plugged in there for us. And then if we hit graph, we can see the actual curve tracing. That was a pretty good model. Right? You guys see how closely it follows those points? When it makes the point dark, that means it used that exact point on the curve. Two. Yeah. All right. So now we actually didn't need to graph it to answer the question. It just says, what is the carrying capacity of Pennsylvania? Like, how many people can you have in Pennsylvania? Okay, 12.579 people? Millions of people. That's how many people you can have in Pennsylvania. Before people run out of food and start eating each other.
Millions.
Yep, because if you look, millions of people. You don't like the S on there?
No.
It's not English.
12.579 million
Yeah.
people. There we go. All right.